Data parallel programs. With the data parallel approach, you partition the data into chunks that are processed in parallel by different tasks. Usually, this is implemented using the SPMD parallel programming model. So here is an example. You take a big data structure, for instance, a 2D array, and you split the array in two subarrays, each subarray being computed by a different task. The properties of this kind of parallelism is that it maximizes data access locality, since a piece of data is usually handled always by the same process. And you have exchanges between the processes only when one task needs the data from another process. Usually we call this kind of approach, the implementation of this kind of approach, an approach based on the owner compute rule. And in the owner compute rules, you allocate a piece of data to one task, the owning task, and only this task can modify or update this data. And all the data that are not distributed are replicated on all the tasks. Let's look at a concrete example. We have a code in here that is computing some data over two arrays, my big data array out and my big data array in, and some coefficients that are. This is a standstill computation. In this computation, I also added a checksum. So we can check that over the parallelization we are not killing the computations. I mean, we're not computing wrong. And I use here unsigned int addition because it's associative and commutative. So even when I will parallelize this operation, it will still get me the same result. So I will be able to compare the the sequential execution with the parallel one. So that's my first code. What I do next is to add the MPI setup in here. Okay, this setup. And in here I'm not doing much, and everything is still performed. All the computations are performed redundantly. So I didn't change anything else in the code. I just have now two processes, and I just add this guard, so I only get one process to display the checksum. What I do next is to start to parallelize, but I'm not yet splitting the data. I'm just parallelizing the computation. So I have again a guard. If I am the master in here, I will do this. If I am the worker, that's for the worker, the master. If I am the worker, I will do this part. And I'm not splitting the data yet, because that operation, if I mix changing the data structure and changing the computation at the same time, I will maximize the risk of doing something wrong. So what I'm doing in here, I'm splitting the computation over only this dimension, which basically split over this one. So the master is going to compute for the first dimension from 1 to data size divided by 2, and this one will compute on this dimension from data size divided by 2 to data size minus 1. Notice that we start from 1 to minus 1 in here, because we have in the array access there is some minus 1 and plus 1, so I don't want to go out of the array. In this example, you can also notice the MPI barrier here. They are not strictly necessary in this code. It's just because I want to make sure that when I start to compute the wall clock time, all the processes are at the same point. And in here, I get the end timing after the barrier, so I know all the processes in my program are done. In here, we are just considering 2 MPI processes, which is obvious from this code. So the next step I still have to do is to split the data in 2 parts. Because right now, each process has the full data in each task. So I change the declaration. Now I have to put data size divided by 2 plus 2. Why plus 2? Because when I split the array in 2 parts, I have plus 1 and minus 1. I need to be able to access this in here. That's actually the same thing as this part in the other part of the array. So I need this plus 2, and what I do to have some mechanical approach to that is actually I just shift the array accesses. The compiler will remove all this extra computation. There is no worry on that. And I only have to change the worker loop because the master loop is computing the left part of the array. So I'm just changing in here, shifting the array access left, and I do that systematically on all the accesses. Again, the compiler takes care of this extra computation, so it's no problem at runtime. And if I run the code, here is the initial checksum, and after parallelization, I get exactly the same checksum. I have 2 cores on my laptop. I run with 2 cores, and as you can see in here and in here, I get a speed up of almost 2, which is what you would expect from this. And because I have my barriers before and after, I know my timing as I'm really counting all the process, the timing for all the processes. Okay, the questions for the classroom. So SVN, the transpose exo code, and what I want you to do is to do the same thing I've just done and to get a parallel version of the transposition code. I just want a naive code. I don't want an optimized code. Just do something simple. And second question is, what is your opinion on load balancing for data parallel programs? What are the caveats here? So, see you in class.